should be able to try to share.
Yeah. Do you see my desktop?
Well, I see.
Okay. Let's make full screen. Now you have my slides.
Yeah, you can see it, yes, but you can make also full screen, please.
Now it is full screen.
Yeah. Now it's perfect. Yeah, thank you. Yeah, so please start.
Okay. First of all, I would like to thank the organizers of the workshop for inviting me to talk about the doubly heavy baryons, tetraquarks and pentaquarks, and address some of our recent works which were done in collaboration with these people. You see. This is the outline of my talk. I will have a brief introduction, then I will go over the doubly heavy baryons, which in the previous talk, Zalak had more comments and discussions about these baryons. Then I will continue with tetraquarks, pentaquarks, and I will have finally some concluding notes. So I start with the QCD Lagrangian. Here you see the Lagrangian. This Lagrangian is, in principle, is responsible for extraction of the dynamics of the quarks and gluons at high energies. But in low energies, at which the hadrons are formed, this Lagrangian cannot be used, and because the coupling constant between the quarks and gluons become large and the perturbation theory fails. So we need some non-perturbative methods to address and calculate the properties of hadrons made of quarks and gluons. There are many non-perturbative methods developed by different people. Here you see some of these non-perturbative methods. We use QCD sum rules as a powerful and applicable method to hadron physics in our calculations. This method, which I want to introduce it schematically in a very simple picture. It was developed by Schiffman, Weinstein, and Zakharov roughly 40 years ago. In this method, this method was developed by many people, and we have many versions of this method right now, like QCD and etc. In this method, we look at two hadrons, which are composite objects made of quarks and gluons, from two different windows. In the first window, we are in low energies and large scales. So we see a hadron with hadronic parameters like mass, its decay constant, lifetime, and in the case of interactions or decays, we have the form factors of the hadrons and etc. In the second window, we go to higher energies and small scales to see the ingredients of the hadrons, the quarks, gluons, and the interaction of quarks and gluons with the QCD vacuum, which consists the non-perturbative effects and have a large contribution to the calculations. Under some conditions and using the quark-hadron duality assumption, we match these two different windows to find the QCD sum rules for the physical quantities. By this way, we relate the hadronic parameters into the fundamental QCD degrees of freedom. Are made of quarks and gluons, and we have two main categories, the standard hadrons and the exotics, which are in the agenda of different experimental groups nowadays. Using the quark model proposed by Gelman and Zuig, we are successful to describe the properties and the formation of hadrons and their properties at colliders. But very recently, we have a rush of excited states discovered in the experiment, and in some channels, the resonances have very close masses to each other, sometimes 10 to 12 MeV. So it is very difficult to assign and fix their nature and quantum numbers using this model. But we try to do that experimentally and theoretically. For the standard hadrons, which made of, are categorized into the mesons and baryons, we have these nice configurations for different types of mesons and baryons, which Zalak discussed these pictures in the previous talk. For the exotic states or non-conventional hadrons, we have tetraquarks, which appear either in a mesomolecule form or a compact tetraquark made of a diquark and anti-diquark. And we can have pentaquarks consist of either four quarks and one antiquark, or a molecule of a baryon and a meson. So we can have also the compact hexaquarks like this and dibaryons, which are molecules of two baryons. Also, we can have hybrids. Here you see, in addition to a quark and antiquark, we have one valence gluon inside the hybrid mesons. And also can have the blue balls, interesting, not only gluons, but gluons are massless, but we have about 2 GeV mass predicted for these globals. So I will go faster over the doubly heavy baryons. When we look at their category, their configuration, they are made from a heavy diquark and one light quark. So when the two heavy quarks are the same, so we can have the diquark with the spin 1. Such baryons are symmetric with respect to the exchange of the two heavy quark fields. But in the case of that we have different heavy quarks, in addition to the spin 1 for the heavy diquark, we can spin 0 also case by adding the third light quark. These doubly baryons takes the total spin 1/2. And these baryons, the variations of these baryons are anti-symmetric with respect to the exchange of the two heavy quarks. So you may look at our papers about different aspects of spectroscopic parameters of the doubly heavy baryons in these papers. Only I want to show the mass results which have been obtained using the QCD sum rules for different members of these baryons. Here you see for these baryons, which also Zalak discussed these spectroscopic and mass values. In 2017, the LHCb collaboration announced the observation of the doubly charged Chi-CC++ with two plus charge of this baryon. And measured its mass around this value, 3,621. The LHCb observed this state in this process and the invariant mass of lambda c plus k minus pi plus pi plus. And this is the resonance by the LHCb collaboration. But was it a new discovery? The CELEX collaboration was the first collaboration in 2002 that announced the observation of the same baryon, but with one plus. The measured value by CELEX collaboration, which was then confirmed in another process in 2005, was about 100 MeV, smaller than the LCB result. In 2012, we calculated the mass of baryons and understand that the SELEX result is very small, and the central value should be relatively high. So, as I said, the LCB collaboration in 2007 measured its mass and found this value. Now we have a puzzle for this state, because in the case of other hadrons, only it is not acceptable this, to have a 100 mega electron volt difference between different the results of different various experiments. So this is a puzzle now in the field of doubly heavy baryons. But when we look at the particle data group, we see the mass reported by the LHCb for this state. These are very important states, these heavy baryons. For example, in the case of the discovered KCC state, it participates in a process which is called theoretical quark fusion. For details, you may refer to this paper. But when we combine the two lambda C baryons to make a virtual 6-quark cluster, it decays immediately to a KCC, doubly heavy, doubly charged, and a nucleon with a large amount of energy, which is more powerful than the hydrogen fusion. But we have difficulties with the lifetime of these objects in the experiment. The LHCb continue to search for other members. Very recently, in 5 September 2020, this paper was published by LHCb collaboration. They looked for this member, Chi0BC, but they found no significant access. Only they put some upper limits on the related parameters. We need more information on different aspects of these baryons to clarify and internal organization and help the experimentalists in the course of search for these baryons in future. In this direction, we took into account these baryons and calculated their strong constants to lie to the mesons in two papers. The vertex does in final baryons with two pseudoscalar meson is parameterized in terms of a strong coupling constant. These are the spinors. We use the symmetric and anti-symmetric interpolation currents for baryons to calculate the strong coupling constant. These strong coupling constants are fundamental objects that can be used in construction of the strong potentials among the doubly heavy baryons with light mesons. So to do that in our method, we start with the correlation function and use the light conversion of the QCD sum rules. Here you see the time ordering product of the initial and final interpolating currents at two different points, and we use the distribution amplitudes of the pseudoscalar mesons to calculate this correlation function, as I said, in two different languages. Then by mapping two languages and representations, extract the values of the strong coupling constants. In fact, we calculate such diagrams, which is this is the leading order diagram, and these are the gluon exchange diagrams. In our relations and some auxiliary and helping parameters enter to the calculations. Using the prescriptions of the method, we fix their working windows for the Borel mass square and the continuum threshold. The strong coupling constants for different vertices, as you see, with different light pseudoscalar mesons. Our results may be by various non-perturbative methods and in experiment in future. We also considered a strong interaction of doubly heavy spin 3½ baryons with light vector mesons in this work. This vertex is parameterized in terms of 4 different J1, J2, J3, and J4 strong coupling constants. Here you see our results for different possible vertices. As I said, may be checked by other non-perturbative approaches. So I will continue with the tetraquarks and pentaquarks. Here, in the case of tetraquarks, here you see some famous candidates which were discovered by different collaborations, Bell, Selex, LSTB, Bestri, and other collaborations. For a history on theoretical and experimental aspects of the discovery and properties of these tetraquarks, you may refer to our papers, in these 2 papers. So we have a problem with these states. Despite a lot of theoretical and experimental studies made in last 2 decades, but unfortunately their structure or clone organizations still are unclear. As an example, I take into account the 39 state discovered by Bestri collaboration in 2013, and then confirmed by Bell collaboration in the same year. We calculated its mass and width using our method and compared with the experimental data. To do to calculate the into J psi plus and eta 0 plus in this work. First, we calculated the mass of this particle using a two-point correlation function. You see the interpolating current for Kirtan and annihilation is baryons between the 2 vacuum states by using these 2-point sum rules and assigning this quantum number, the total angular momentum charge as plus minus. And by considering these quantum numbers, we write, and also considering the quark content, we write its interpolating current made of 2 quarks, a diquark and a anti-diquark. This is the interpolating current defining this state. By using this information, we extract its mass, which you see with its error, and compare with the experimental data. Here we have other results of other theoretical works. Here you see one of them. All of these are consistent on the mass of ZC state. We predicted its constant, decay constant, which is one of the main inputs in calculation of investigation of the decay properties of this particle. Its mass, I said, we considered its decay to a psi pi and eta c rho plus, and calculates diagrams of vertices, which is defined. This vertex is defined in terms of only 1 strong coupling constant. By calculating the exclusive widths of these states, we estimated it to be 61 plus minus 10.6 MeV, and these are the data provided by Bell and Bestri. We compare the mass results and also the width results with the experimental data, these comparisons led us to consider that the ZC, the discovered ZC900 state, can be considered as a hidden charm made of one charm and one anti-charm quark and axial vector tetraquark with the quantum numbers that I showed you. Very recently, we investigated its properties in a cold nuclear matter. In this case, we have the same correlation function, two-point correlation function with the, for its nuclear matter here. When we plot the mass ratio of this state in medium to vacuum mass, we see that in terms of the density, its mass starts to decrease. These are the Saunders predictions which are valid up to 1.2 rho saturation density. Then using different fits, we can extrapolate the results to the higher densities to up to 5 times rho saturation, which corresponds to the density of the core of the neutron stars. These results may help experimentalists also in heavy ion collision experiments and experiments that are done in the medium, in dense medium. Finally, these efforts may help us to fix the nature of these states. I will continue with introducing another tetraquark, which in February, which is announced by D0 collaboration in 2016, announced the observation of a new tetraquark, called it as X5568. This was introduced as the only particle made of 4 different quarks. So they can be either in the mesomolecule form made of B and K mesons, or it can be, it could be in the compact tetraquark form made of a diquark and anti-diquark. And the experiment fixed its quantum numbers and found that it is a scalar particle of positive parity and positive charge. So this is the resonance picked by the D0 collaboration in the invariant mass of BS0 pi plus minus. So this is version of the D0 paper you may see in the archive. They announced this as observation of a new state, but the CB and other collaborations later could not find any significant access, and only the D0 collaboration later also confirmed this state by in another process. But the final version of the D0 paper, which was published in Physical Review Letters, when we look at the final version, they changed the observation to an evidence. Now, further experimental analyses are needed to answer the question whether this state exists, does exist or not. And in the theoretical side, there were a lot of papers studied by many groups, and we were one of the groups that discussed, that investigated this state in a couple of papers. In this paper, our first paper, which published only 2 days after the D0 announcement, we estimated its mass by considering these quantum numbers and this assumption for its structure. We constructed a current, a scalar current, and found its mass with this value and the experimental value. When you compare, we see good agreement between these two results within the errors. So we also estimated its decay constant, this value, and then we investigated its widths, considering its strong decay to BS0 pi plus, and found this value for the its widths, which is comparable with the D0 result for the widths. We also predicted the mass and other properties of the charm partner of this state in two different scenarios. We have these masses predicted for the charm partner, but around 2,600. But the LHCb collaboration very recently, in August 2020, announced the discovery of the first open tetraquark, which called it as X2900. This particle is made from up, down, strange, and charm quark. And this was the first tetraquark made of 4 different flavors discovered by the LHCb. Actually, LHCb found another resonance near to this resonance. The first one was a scalar state, and the second one was a vector state with these properties, mass and but the mass, their mass was around 2,900 and very high compared to our predictions made in our previous works. But their structure were different compared to our previous prediction. So in our recent work, we took into account the scalar case and assigned the molecule structure for that, calculated its mass and width in this paper, and we found its mass and width comparable, this time comparable with the LHCb data. In our previous works, we considered the charm case as in the form of a compact tetraquark, but this time we made an assumption that it is a Coulomb D star bar K star mesons. So I continue with the pentaquarks. Pentaquarks have a long experimental history, as everyone knows. One may refer to one of our papers for this long history, but only I will mention some recent states, pentaquark states discovered by the LHCb collaboration. In 2015, the LHCb announced the observation of these two pentaquarks, PC4380 and PC4450 in this paper. And this is the process that the LHCb discovered these two pentaquark states. So after the discovery, we again used the QCD samples to predict some spectroscopic properties of these states. For the state 4380, we assigned this total angular momentum and considered it as a molecule of D bar star meson and sigma C baryon. And for the other one, we assigned a total angular momentum of 5.5 and consider it as admixture of two molecular states of mesons and baryons. Using these structures, for their nature, we predicted the mass or decay constants of these states for different parities. Two of them are comparable with the were comparable with the experimental data provided by the LSCB collaboration. For the others, we may search in the experiment. Also made estimation for the properties of hidden bottom pentaquark states with spin 3½ and 5½. We found that their mass should be around 11 GeV, and the LSCB now searches for these states. In 2019, the LSCB collaboration announced another observation of a narrow pentaquark state, PC4312, and also splitted the previously seen 4450 states into two peaks and called them as 4440 and the pentaquark 4457. Now we have in total four peaks and 4 states discovered by the LSCB collaboration, and we need more works to clarify their name. As our final calculations, very recently we considered this state PC4312 in this paper, and we considered it to be a molecule of sigma C++ and D bar minus state with the quantum number 1/2, with total angular momentum 1/2 and parity, negative parity. We consider such a molecular interpolating current for this particle and calculated its mass and found this value, which is very close to the experimental one. We also compared our results with the other theoretical predictions. Most of the theoretical predictions have assigned the GP equal to 1/2 minus for this new state. So this brings me to the concluding notes. So we have made a good progress on the identification of doubly heavy baryons in the experiment, and we hope we will observe more states predicted in the quark model. Although we have recorded good experimental and theoretical progresses on tetraquark states, but the nature and quantum numbers of most candidates have not been, unfortunately, exactly fixed. So, and we need more theoretical and experimental studies on the discovered pentaquark states to clarify their nature and internal quark-gluon organization. Thank you very much.
Okay, okay, thank you, thank you. What about questions? I cannot see. Okay, no good. No questions. Okay. Thank you very much. It was beautiful report about new object for tetraquark and pentaquark.